On Developer Voices today, we're talking about distributed systems, clusters of computers working together. When your software spans more than one machine, or sometimes even more than one country, how do you get it to behave in a safe, sane, rational way? How much of that problem should you push out to the database? How much of it is in the hands of the application developer? To discuss it all, I'm joined by Benjamin Bengfort, who has a really interesting career that we barely had time to touch on. He's worked on self-driving vehicles back in the early days. He's worked on detecting bombs via their 3G signals for naval intelligence. But in his 30s, he went back to school to get a doctorate in globally distributed systems. And that's what we really talk about in this podcast. I started out by asking him, tongue slightly in cheek, surely we just use Zookeeper and that's the end of the problem. But by the end of our conversation, he has me completely convinced the most fun thing I could do next is write my own distributed consensus mechanism. It's always seemed a bit like encryption, one of those problems where maybe you shouldn't roll your own. But Benjamin has persuaded me. The time is ripe to dig into distributed computing, bypass the off-the-shelf stuff, and build some software that's genuinely tailored to the problem that you're dealing with. I'm inspired. I'm inspired to do some hacking, and I hope some of you will be too. So, let's do it. Let's go from here in the UK to there in the US, spanning the globe to talk about software that can span the globe. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Benjamin Bengfort. I'm joined today by Benjamin Bengfort. Benjamin, how are you today?
I'm doing well, thank you. Glad to be here.
I'm glad you're here because you're going to take us to school, which is going to be fun. You're our Developer Voices resident distributed systems expert.
Oh, that's such high praise.
Yeah, it comes with a badge and a little blazer lapel pin and that kind of thing. Excellent. So I'm going to start with a deliberately challenging question, if I may. I think we can probably all agree that there are times when you need to grow beyond writing to one machine, right? So distributed systems are kind of inevitable past a certain size. But why don't we isn't the answer to distributed systems install Zookeeper and forget about it because it's now someone else's problem?
And that actually is the way that many distributed systems are built. I think that's a fairly common architecture. Zookeeper, etcd, plus some distributed storage system like Ceph underlying it. And then what you end up with is a single node system that can be placed by Zookeeper, right? And so you've turned your distributed system into maybe a sharded or sort of multi-part singular system, and now you can reason about the consistency on that shard. But the problem is that you've lost some of the gains that you've made by distributing the system in the first place, right? So if the why of distributed systems is we want things like fault tolerance, right? So we want to survive failures. We want to have high availability, which is a really loaded term. But for me, high availability is you might have people in North America, you might have people in Europe, you might have people in South America. You want the servers that they're accessing close to them, right? So that they can get access to their data. That's kind of a different definition of high availability, right? But you want that access close by.
Yeah, the definition I always want to go with high availability is if something explodes at 3 a.m., do I get woken at 3 a.m. or can I roll in at 9 a.m. and fix it?
Yeah, and actually that's like the engineer's perspective or the academic perspective. But when you're building applications, you're thinking about your user. So maybe that's the problem, right? That the disconnect between just using Zookeeper is that you have people who are thinking about the systems, and then the people who are using those systems are thinking about the users. And there's a disconnect.
Right, yeah. So maybe we do need to delve a bit beyond just solving it off the shelf.
Absolutely. User-focused distributed systems.
I like that.
Yeah.
That could be the title of the next book you write.
That would work. Yeah.
Yeah. Okay, so I know you have this theory about the history of distributed systems as being like a pendulum between weak and strong consistency. I think you put it.
Yeah, I mean, I think that's true for a lot of technologies, right? Especially when you have trade-offs that you have to deal with in technology. And I think the hope is that the pendulum will swing from one extreme to the other and then swing back, but not as far, and then swing back, but not as far. And then hopefully by doing this sort of walk back and forth, we find some, trade-off middle ground that's optimal in the generic case. Consistency is no different. And I think studying history is incredibly important, especially with the messaging that happens around these types of systems where they're sort of said, like, these are brand new ideas. And then you have someone else who comes in and says, no, these are not brand new ideas. But yeah, what's really happening is, you start off with distributed systems, you want to scale. So you make weak consistency guarantees in order to scale. And I'll start at Bigtable, maybe sort of early 2000s with this talk. But this also happened in the relational database community. So as far back as the 70s and 60s, you're talking about consistency and isolation. You have a whole sequence of events that's going on in the relational database realm. And then we restarted it again in maybe the NoSQL realm. I don't know if I want to call it NoSQL, but in sort of the new version of distributed systems that happened after the .com bubble popped, and now there was all this dark fiber and available serverware that you could, the Google and sort of the big tech guys took real big advantage of right at the beginning.
Yeah, when we reached the point where having lots of machines was just the cost of it was easy, and the software logistics of it were hard.
Exactly. Yeah. And, the hardware changes, also are a big part of the story, right? Things are getting faster, cheaper. You can have bigger clusters, right? Virtualization, there's a whole other side story to this.
Yeah. There was definitely a time in our history when people didn't think about distributed systems because being able to afford 2 computers was beyond the realms of imagination, right?
Yeah. And that's how the relational database community ended up, right? They ended up in like a vertical scaling model. Right. Yeah. Because, horizontal scaling was supercomputing, type technology in sort of the late 80s, early 90s.
Yeah.
But so once Google has Bigtable, sort of a weaker consistency model, and it works for them, right? It works for their advertising portal, but they say, hey, let's generalize this and give it to other people to use. Other people start to use it for their applications, but they can't reason about the consistency semantics in Bigtable. So now you swing back the other direction to stronger consistency models. And, at the time, I think it was, data warehousing, things like Vertica, Hadoop with a very strong consistency semantic with HDFS. But now our systems are too slow, right? So you swing back, right? And now we're in sort of Dynamo land and thinking about Dynamo and S3 and more eventually consistent models. But again, the people who are building applications on top of these things, they don't know or understand distributed systems because that's not their job. Their job is to build a web application. And so the consistency semantics are creating bugs or problems that are very costly for them. And so you swing back into things like Spanner and, and so it keeps swinging back and forth, this consistency pendulum. And right now, where I'd say that we're at is we're in the new SQL phase. I think is what it's called. New SQL, where everyone is trying to do distributed SQL transactions. So give application developers a consistency semantic that they understand, SQL and isolation levels, but do it in a distributed fashion.
This is the rise of things like
and other things come in.
Yeah, all these different databases that aren't relational databases, but want you to access them with SQL.
Right? Yeah, and like Postgres drivers.
Yeah. Don't look under the covers because honestly, it's a lot more complicated than you want to think about.
Exactly, and the consistency problems do pop up. Aurora is notorious.
Yeah, sometimes that's the worst thing when it behaves mostly like a consistent system, and then there are edge cases where suddenly you need a degree to understand what's going wrong.
Yeah.
But maybe we should step back a bit and say, because you've said weak consistency and strong consistency. Maybe we should define those.
Okay.
To know where we are and then move forward from that.
Yeah. So first, what I want to say is I personally believe that consistency is a continuous spectrum between weak and strong. And that's an academic opinion of mine. And there's an academic debate about whether that's true or not. I point to two things to talk about that. So first, Cassandra will actually, on a per query basis, let you choose how many replicas are involved in the read and write query. So one of the ways that you might think of consistency as a spectrum is that, if you have a 30 node Cassandra cluster, which kind of ridiculous, but if you did, and you chose one replica for your read or your write, that's the weakest possible consistency that you can get. Whereas if you choose 30 replicas in that cluster, you now have the strongest possible consistency that you can get. And then any number of read write replica sets in between, you get this sort of varying consistency over time.
So is this what we're saying, that like in a distributed system, you write some data, inevitably the data ends up first on one machine?
Inevitably, yeah.
And then it's spread across the cluster, and by the time you come to read it, are you going to get the same answer regardless of who you talk to or not?
I mean, I think that's a good definition of consistency. So even before we get into like what is weak and what is strong consistency, maybe we should talk about consistency.
Yeah.
Folks who are used to databases probably recognize the C in ACID as consistency, but in distributed systems, it's actually C and I, right? It's isolation and consistency. So it's not just data consistency, it's also what is the experience of one user querying the database from an external perspective.
Yeah.
So broadly, what you might say is, given a system of more than one replica and just treat it as a black box, if you give reads and writes to the system, are you always going to get the same answer from two different concurrent clients? Right? That's what consistency is.
Yeah.
And so in a weak consistency, like if you have two replicas, replica A, replica B, and client 1 connects to replica A and writes to X, and client 2 connects to replica B and reads from X, and then client A reads from replica A, they're going to get two different answers for what X is, unless replica A and B coordinate somehow to ensure that that write is the same thing that they see.
Yeah.
And that does kind of translate to isolation. When you talk about read committed, snapshot isolation, that kind of stuff.
Can you read your own writes, that kind of stuff?
Exactly, read your own writes. But it's also, that's more about transactions, but it's also about just sort of the data consistency model. Like, have we violated any invariance? Like, if X is a number, should X always be greater than 0 in sort of the classic accounting, ATM transaction case that a lot of people like to talk about in school? Or if it's a unique value, what happens if one person writes to X on A and one person writes a different X to B, and it's supposed to be unique? One of them is supposed to get an error back. This wasn't unique. But if A and B don't know about X, then they're both going to succeed. And you've violated the C in ACID in that case. You violated the uniqueness constraint.
And plenty of systems, even like modern systems, say the way to solve this is to have concurrent readers, but a single writer.
That is one way to do it, certainly. This is sort of the high availability Postgres model, right? Where you have one read-write Postgres replica, and then you have a lot of standby replicas is now the terminology. And you can have standby replicas that can take over if the first one fails. That's mostly fault tolerance. Or you can have standby read replicas, so that you can have that sort of high availability, you can read from those replicas. But you do introduce an inconsistency in the form of stale reads in that case, right? So if replica B is a read-only replica and it's behind the read-write replica, you can read something that's not current, right? You can read something that's untrue.
Yeah. So you end up, the main server is in San Francisco. You're reading off a replica in Australia, because that's where you are, is delayed. But then when you go to post a new transaction, that has to go over to San Francisco, because that's where the writer is.
It is.
and you could end up reading your order history, and the order you've just put in hasn't made it around the round trip by the time you do that.
Exactly. And it introduces the transaction problem again, because if you want to read then write, which is a very common operation, you can't read from one replica and then write to the other. You have to do your read then write on the primary.
Yeah. And then do you push that into developer space to make sure they're handling those semantics?
And so now your Australian user has a worse experience than your San Francisco user. So what was the point of distributing the system in the first place?
Yeah. It's faster, but it's also more wrong.
That's true.
And that's actually, I say that facetiously, but is that ever the right trade-off? Faster but wrong?
Yeah, absolutely. I do believe that's a good trade-off, right? I think that a lot of people want to say like strong consistency is the thing that we want, right? Mm-hmm. And we haven't even talked about weak versus strong, but there was a reason that Bigtable was successful. There's a reason that Dynamo and other eventually consistent systems are successful, and that's when collisions are rare, right? When it's a rare that two clients are going to be working on object X at exactly the same time. And when collisions are rare, a weaker consistency system does improve the performance, availability, and fault tolerance of the overall system. And you just have to somehow deal with those collisions, downstream. And if you can do that at the application level, then this weaker consistency system behaves better overall. But what that means is that the application developer has to know what the semantics are of that weaker consistency model so that the application can deal with it. And that's where the gap is.
That always seems tricky, because it always seems like when we buy into a distributed system with those semantics, we start off trying to follow the rules. And 6 months into developing the project, we start to behave like everything works the way it does in development.
Right.
Because everything is always completely consistent in development, right? Because the network's so small and fast.
Yes. Or you're just developing on a single node, which is even worse. I think one of the issues is that, in the case that I just talked about, where collisions are rare, they're even rarer in development because you're not pushing the system as hard as you would be in production. Yeah. And then even in production, they're hard to notice, right? Like if we talked about this, client A reading X and client B reading X, client A and B have to talk to each other in order to figure out that something went wrong, right?
Yeah.
They can't just sit there and be like, oh, this is a consistency problem. You know what I mean? Like, it's really hard to observe consistency problems, generally speaking.
It normally ends up that you just get weird behavior that the users are complaining about, and then you realize. And that's a horribly far down the pipeline time to find out about these problems.
It is. And distributed debugging of consistency problems is horrendous. etcd recently had a massive bug that was a consistency-related bug. And the way it manifested itself was it kept overwriting decisions that it already made, and it kept that, basically in these very few, very rare cases, etcd would fill up its storage volume and then blow up. And there's a great KubeCon talk about this from last year's KubeCon 2022, KubeCon in Detroit. So if you're interested in that bug in etcd, I do recommend that video. And
I'll put a link to that in the show notes.
Yeah, absolutely, Alan. I'll send the link to you. But so anyway, this problem is happening, and everyone is trying to debug it, and no one can figure out what's going on. And is it on the application side? It's clearly an etcd problem. etcd is running Raft, right? And so everyone's looking at Raft like, did you do something wrong with Raft? Is it the strong consistency system? Is it something wrong there? Is there a bug with the invariants? Is Raft not safe? But it actually turned out to be the consistency of the level DB transaction that's under Raft when it's writing to disk, right? They were actually opening two concurrent transactions to write to level DB and not closing one of the transactions. And so one transaction would beat the other transaction, and that's what was causing this failure. So, But, back to the sort of original point was just like, the weird thing that we saw was etcd filling up its storage volume. But how do you diagnose that, right? Like, how do you, and it's so rare, like it only happened in these few cases. Like tons of people are running etcd successfully in production without this, very edge case, very low probability occurrence happening. And it's very difficult to fix. And if you watch the video, the story of how they found it and fixed it is months worth of effort and heartache. Yeah. So it's important to get it right when you start.
As ever. But you can't just say that without giving me some guidance and hope.
That's true. That's true.
Because the thing that makes this really hard is I think our brains are hardwired for linear time.
Well, that is extremely philosophical, and you're right. We think in instances of time.
Yeah.
And when you ask me to describe weak versus strong consistency, before I even define those things, I started in with, consistency is a spectrum. But we as developers, we still think about these positions on the consistency spectrum, right? There's weak consistency, there's eventual consistency, there's causal consistency, sequential consistency, and then linearizability. And I agree that we think in linear time, but we don't think in linear time like I'm not thinking in your linear time. I'm only thinking in my linear time. And so, but the two of us are talking concurrently, right?
Right, yeah.
And so as a developer, like how do you develop a system where there's multiple actors in the system that have to linearize some sequence of events? And obviously they can coordinate just like you and I can coordinate, but there are two separate linear streams of time.
So you're saying our first step is to imagine ourselves in a crowd?
Yeah, absolutely.
Yeah. So
as
take me through.
How about dancers? I think dancers is a good analogy. That's actually how I prefer to develop. There's actually two, I think, models of distributed systems development. So the one that I subscribe to, I suppose, is very close to the actor model.
Okay.
But what you do is you develop a single node, right? Which implies that you're going to have a homogeneous system of all of these same nodes, right? And you think about the behavior of that node. And what you want to do is you want to come up with the simplest set of behaviors on the replica so that when you add them all together, you get more complex behavior, right? So from simple local behavior, you get global emergent behavior.
Yeah.
So in the dancer analogy is you think about the choreography for one dancer, and sure, it looks great when there's one dancer, but if you put 20 dancers and they're all doing the same choreography, it looks amazing. Right?
Yeah.
Right?
Yeah, this
so
is
that's kind of the one model I follow is that actor model.
This is, I'm reminded of something Louis Pilfold said to me recently. It's like, it's easier to write a reliable web server for one request and then make 1 million of those than to make a web server that can reliably serve 1 million requests.
Yeah, exactly.
Yeah.
That's exactly it. But that's not the only model. So then there's the specialization model or the specialist model, which is kind of the other model of development. And in the specialist model, you say, okay, we're going to think about these different roles and responsibilities, and here is the responsibility for this type of replica. Here's the responsibility for this type of replica. Here's the response, and you have specialization. And that might be more akin to like a cheerleading squad, right? Where you have people who are doing the lifts, and you have people doing the flips, and you have people who are getting lifted, right?
Right. Okay. Thank you for taking me through that, because we don't have cheerleaders over this side of the pond.
Gymnasts, I guess. I don't know. Or a dance that has maybe more complex components to it, like modern dance versus something else. And like, if you actually look, we can take this back to the distributed systems. Paxos is the specialization model of development. So Paxos, you have replicas, acceptors, leaders, commanders, scouts, right?
Oh,
You have
really?
all of these specialized roles in Paxos, whereas Raft is the actor model, right? Raft, you have one replica, here's what it does. It can become the leader, but it can also then go down to becoming a follower, right? So Raft versus Paxos, you can see those two different styles of thinking about developing distributed systems.
Right, because I'll check my knowledge here. The Raft and Paxos, the surface differences, they behave exactly the same. Paxos came along and it did all this like leader election stuff. Raft came along and said we can do exactly that, but you'll understand the algorithm better.
I mean, I think that was certainly Diego's goal was understandability. And Diego Garcia and John Asserhout are the authors of Raft. I think I might have gotten Diego's last name wrong. Diego. Yeah, anyway. Hopefully you can cut that out.
I'll have a subtitle caption on the YouTube version that corrects it for you.
Sorry about that little brain fart. Yeah, I mean, that was certainly the goal of Raft was understandability, right? And even the name of the paper was a more understandable consensus algorithm. And, you know, I remember the initial way that this went about was they taught Raft and they taught Paxos, and then they gave a survey to students that they were teaching to see what they understood to show that Raft was more understandable than Paxos. But you know, they're the same in the sense, you know, if you think about multi-Paxos, where you have a leader that can cover multiple slots, or multiple ballots, versus.
Sorry, what does that mean?
Well, so Paxos is all about safety and theory, right? You know, Lamport defined Paxos thinking about safety, you know, and thinking about these multiple processes that we're running. So replicas have slots, and the slots hold commands. And what the goal is to have replicas have the same list of commands in all of the same slots. And the way they achieve this is by asking a synod, which is, all of these terms in Paxos, they ask a synod to decide what command should go in one slot. And the synod does that with balloting. So slots and ballots are kind of different, although whenever people think about Paxos, they always unify them. Right. So they are a little different. Whereas, you know, Raft is about a single, totally ordered log of commands, which obviously is a simplification of the Paxos model. And then Paxos has all of these invariants for the different roles. You know, for leader, you know, acceptor, committer, you know, proposer, scout, commander, all these different roles have all these different invariants that they have to follow. And Raft replaces many of the invariants with timing, right, and timeouts.
What does that mean? Take me through that.
So Lamport has this idea of sequential consistency, right? And if you are a distributed systems academic, you don't believe in time, right? there's no such thing as time, right?
Once you've got tenure, I suppose that's a natural response.
That's right. Yeah. So instead of time, what you have is you have things happening before something else.
Okay.
Right.
Yeah.
So, you know, this happens before this happens before this. And if you have two events that have no relation to each other, it just means that you can't establish a happens before ordering. So in distributed systems, you don't have time, you have the ordering of messages that are received by the system, right? So, you know, you don't put a timestamp on it because my clock could be different than your clock. So you instead, like, I got this message, then I got this message, which implies a total serializability of messages, which is one very big bug that a lot of people who are just writing distributed systems make, is they forget that most web servers parallelize requests and request handlers.
Right. Yeah.
So you have to have this sort of sequential ordering of messages in order for all of this to work. And so Raft says, okay, you know, that's fine. But, you know, broadly speaking, at a higher level of time granularity, you can, as long as we're at like the millisecond level or the second level, that level of granularity, we can have timeouts and things in order to control these roles and responsibilities. So there's, heartbeat timeouts and candidacy timeouts that control what roles each node in the system has, as opposed to Paxos, where you send a bunch of messages out like saying, hey, I would like to be the leader for this slot. And then if you get enough responses saying, sure, you can be the leader for this ballot, then you proceed. But if someone else says, no, I'm actually at a higher ballot, then you kind of flip-flop back and forth. And it's all about the timing of messages so that one node, like all the nodes get the messages at the same time in the same order, rather than just actual clock time.
Right. Already this seems very hard to implement in practice.
Yes, and there's a whole lot of academic literature that complains about how hard Paxos is to implement.
Did all the complaints come before Raft was written or after?
That's hard to say. A majority of the complaints came before Raft was written.
Okay.
So pre-Raft, I think use Zookeeper, use Chubby, use etcd to build your system. That was the right thing to do, right? Because someone or many someone spent a lot of time dealing with the Paxos implementation, right? And then you didn't have to worry about it. But post-Raft, right, I think it is a little simpler to implement these consensus algorithms. So ePaxos and Raft, with a little bit of time and care, those things are able to be implemented in an effective and safe way.
Really? So you're saying it wouldn't be mad to roll your own?
I don't think it would be mad to roll your own. And I think that we're seeing the effects of that, right? Cockroach has rolled their own. etcd rolled its own Raft.
Kafka recently.
Nats, Red Panda. I mean, like it's not uncommon, right? The HashiCorp has one, Console, so there are tons of systems out there that you can look at the implementation, they're open source, and that you can slightly tweak to your use case.
Okay.
Even inside Raft, we were talking about read versus write. Well, Raft elects a leader. All of the writes can go through that leader, but are you allowed to read from a follower? Yes or no? And actually, if you can read from the follower, then you've got what we talked about originally, which is the read secondaries.
Yeah.
Which you might give you stale reads, but you still have strongly consistent writes. So even when you're implementing Raft, you still can make choices. Are we aggregating commands? Are we sharding Raft? There's still a lot of things that you can do even inside of that implementation. So now, post-Raft, post-ePaxos, we're in a world where I think people can and should explore writing their own consensus algorithms.
Wow. I didn't think anyone would ever say that.
Go ahead and comment. I'm willing to do that, to say that. And okay. We haven't even talked about the eventual consistent algorithms, but, also writing gossip protocols, right? And thinking about, anti-entropy type eventually consistent replication is also another thing people should be considering doing, because what you can do then is you can embed your application semantics into the storage system that you're writing.
Ooh, that sounds exciting and weird, and avoiding all those lovely abstract out your distribution layer things. Exactly. Tell me about that.
One of my favorite examples of this is RQLite, which is Raft SQLite. So it's a Raft replicated SQLite server.
Okay.
And the way that you do transactions in RQLite, and I'm not an expert in RQLite, so but what I looked at this implementation, and what it looks like you do is you take your transaction, everything between begin and end, right, a bunch of commands, and you bundle that all together, and that's one Raft command. And you raft it around, and then it gets executed on SQLite server, and then you find out as a user whether the transaction succeeded or whether it was rolled back.
Right, because SQLite is naturally single-threaded, right? Is that still the case?
I don't actually know if that's true or not anymore, because I know that SQLite has a lot of locking inside of it, and you can actually open a SQLite database now for multiple processes.
Oh, right. Okay. Maybe I'm out of date there. But you're now saying it's possible to do it from multiple servers.
Right. So yeah, RQLite basically makes SQLite a server.
Uh-huh.
And also, just while we're here, SQLite is an incredible technology. I am such a big fan of SQLite. It is really just an amazing piece of database technology, and I highly recommend considering you using it even inside of your Kubernetes clusters, because it's easy to attach a volume and drop a SQLite server there, and then you don't have to deal with all the like HA Postgres stuff, and you still have a relational database under the hood. And it's an incredibly effective tool.
Yeah. Okay. One thing I remember finding out, to my surprise, is that there's a SQLite database in the iOS core libraries.
Yeah,
It
for a lot
really
of
is
mobile
everywhere.
applications make use of it as well. And I think a lot of browsers use something very similar. I think it might be called IndexedDB.
Yeah, their internal HTML5 database. That's
Yeah,
SQLite under the hood most times, right?
or a fork of SQLite or something like that. I don't know for sure, but yeah, I think that it's gotten around. SQLite, Maria DB, Level DB, RocksDB, like there's all these sort of embedded database engines out there that are just available for distributed systems researchers to use, or distributed systems application developers to use, to create higher level distributed systems from.
Cool. Yeah. Haven't we, though? It seems like we've got very firmly into this idea of elect a single writer. And however you do that and however you change who's leader now, we're still doing single writer model.
Yes. And that's certainly one of the ways that things goes down, especially with Raft. And, the leader is a bottleneck, right? And, I'm primarily interested in large geographically replicated data systems. So I like the idea of, someone in San Francisco and Australia and Europe. I want to see how those database systems work. But, in practice, even just having something on, one side of the continent, the other side of the continent can introduce a lot of problems, even with a fiber trunk between them. So, the first method to deal with the leader-based system is to shard the system, right? So you have multiple leaders operating on different tablets of data or different shards of data, and you're running, multiple Raft quorums. And this is how Cockroach works. That's how Spanner works. You'll see basically huge numbers of Raft quorums inside of a lot of bigger distributed systems, and they're just working on different pieces. And one of the reasons that works is, let's say that you have a 3-node system. Well, we know that the leader is doing most of the work, right? The followers aren't doing most of the work.
Yeah.
So what we do is we break our object space down into 3 parts. And then hopefully what will happen is that you will have, part 1 on one replica, part 2 on one replica, part 3 on replica, and they're all sort of leaders for each of their parts. And so you're maximizing, CPU and disk writes across all of the partitions.
Yeah, but how do you generally tend to shard that? Is it like, to simplify, you've got all the accounting stuff in San Francisco and all the user data in Europe,
right,
and all the product catalog in Australia? Or are you sharding it by all the keys from A to M end up in San Francisco?
Or are you sharding it from the provenance of the first write? Which for GDPR compliance or CCPA or the other privacy laws that we have, basically the key space is provenance related. So whoever the first writer was, it has to stay. The leader stays in that region.
That's particularly spicy.
Yeah, exactly. But again, this is just another point, right? Like your application should determine, right, how this is happening, and some database systems might give you control over that, but being it's you're going to get to the use case eventually where your sharding mechanism maybe doesn't exactly match what the database is providing you, and then there's an opportunity to start thinking about rolling your own solution and ensuring
Wow.
that your sharding technique works.
I never thought we'd hit the day when you were saying generally companies should be thinking about rolling their own distributed systems as they grow.
Like I said, it's probably a controversial opinion, but I think that we are in that phase right now. I don't think that phase will last forever, but I think that's what might help us with the innovation that we need to get to the next stage. And frankly, in the early 2000s, that's where we were at then, right? Google was rolling their own, Twitter was rolling their own, Amazon was rolling their own, Square was rolling their own, Dropbox was rolling their own. So, there have been phases in databases and distributed systems technologies where companies thought, okay, it's actually better for us to roll our own. And at the time, those companies that I just mentioned weren't big tech. Like they are now, right?
Yeah.
Back then it was Microsoft and Oracle and Yahoo, and these were the little guys, right? And so now we're back in that same phase again, right? Where now with privacy laws, more globalization, more cloud locations than ever before, right? I mean, 5 minutes and I can have something running in every single continent, right?
Except Antarctica.
Except for Antarctica, that's true. I can't get there quite yet. So 6 out of 7 is not bad, right? But if you look at the planned rollout of these cloud locations, right? South Africa, Northern Africa, Brazil, Peru are getting new data center locations. So it's easier than ever before to just put something up in Japan, put something up in Europe, put something up in India. So we're in that phase where
all the problems that come with it.
And all the problems that come with it. Yeah, exactly. And also we're facing the problems. So yeah, I think you should roll your own. We're in that phase where innovation is necessary and the more people that are working on it, and if you feel enabled or empowered to do it, that's where the innovation will come from.
Right, yeah. So you're more saying that's the next natural swing of this pendulum.
Exactly.
Okay, I think then you have to give me your Benjamin Bengfort guide to writing my first Raft algorithm.
Oh my goodness!
Yeah,
we want to go with Raft in that yeah, writing Raft is easy at first and hard after. Right. So the step number 1 is you want to make sure that there's a single thread, right, or a single place where all messages are handled in Raft, right? So whether you're using gRPC or you're using an HTTP client, your server in the thing that you're embedding, all of your messages are going to be coming in concurrently. And you want all of those messages, whether they're from a client or from another replica, to go through what I like to call one big pipe.
Right.
So Step 1 is make sure that you totally order your messages within your system. And so if you're using Go, channels are great for that, right? If you're using something that has mutexes or something like that, you want to make sure that your central thing is handling one message at a time in as close to the order that they're coming in as possible.
Some kind of software transactional memory thing.
Exactly.
Right, yeah.
Exactly.
Okay.
So step 1 is make sure you've got the one big pipe thing locked down. Step 2 is implementing your timers and remembering that your timers have to go through the one big pipe, right? So you might start to think of these things more like events, right? So a message received from a client or from a replica is an event, and a timer going off is an event. And these events have to be handled in order with one big pipe, right? So one central process.
Okay, so if I'm using like a channels or coroutines thing, I might have one machine that's just responsible for sending heartbeats, and that goes into the coroutine pipeline.
Exactly.
It's not something within my single Raft atom that's time ticking.
Exactly.
Okay. I'm with you so far.
Yeah. So and really, if you do that, you've solved like 80% of the bugs that the undergrads and graduate students who are being taught this usually have, right? Because they usually end up having, lock contention issues or other types of concurrency issues, like concurrency issues between the heartbeat and the networking component, right? So you just want one thing that's rafting, right? One thing that's managing the state, and that goes through. The second thing that's important to think about is you want your Raft replicas to fail hard, right? You want them to die totally, which is another thing that I think a lot of people have problems with, right? So you don't want to get into like a partial shutdown state. You don't want to get into like, partially writing to disk or anything like that. You want things to die and die completely. And so thinking about like, what are you using for your storage under the hood? I personally recommend LevelDB as sort of the storage layer under the hood to start off with, because it's so easy to get started. Or you could use something like BadgerDB that has transactions and buckets. But you want to make sure that you're using something so that you understand the consistency model from that sort of central process all the way on down. And that if something goes wrong or something shuts down, it all just completely goes away and dies completely.
Right. And your partial write gets rolled back, or?
And your partial write gets rolled back, exactly.
Yeah, okay.
Or, you don't, one mistake that people make is like they have like a heartbeat messenger, right? And so every time the heartbeat timer goes off, they send a message, right? But that's dependent on that replica being a leader, right? So if you don't become like if you lose your leadership status, that heartbeat timer needs to stop. But it could be that it sent a heartbeat message because it's an independent process.
Yeah.
So this is another reason, right, that everything happens in that sort of one order of events, right? The heartbeat timer goes off. That middle thing is going to send heartbeat messages, right? It knows that I'm the leader state. It sends its heartbeat messages out. Then the next thing comes in, and this is like, a vote, right? And the vote term is higher than my term. Well, now I've got to go down to a follower, right? Because, the term has changed, right? And I got to get all the messages from the log that I missed, right? And then the next thing comes in, and maybe it's an append entries from the new leader, right? Everything has to happen like one at a time, whether it's a timer message or whether it's a network message.
Right. Okay. And then within that, I'm building like, can I download like the Raft state machine spec and just implement that?
Yeah. So if you go to the paper, right, in the paper, there's like a one-page description of the algorithm, right? It's in blue and red and has like black text, and it's just like a box. And it says like, this is what a follower does. This is what a leader does. Here are the invariants. Here's when you should be setting these messages. Here are these timeouts. It's just one page. You can pull up that page, and as long as you get the things right that I just said, more or less, you will end up with a working Raft system.
You make it sound so easy.
I don't want to imply that it's easy, but with like a little effort and a little consideration, I think that it's buildable, it's doable.
Okay.
And it's a fantastic exercise, even if you're not going to put it into production on your own, for just understanding the semantics of a distributed system.
Because there was a time I would have said anyone attempting to do that was mad. You're now saying it's a sane thing to do.
It's sane. Now, the devil's always in the details, right? So I've tried to head off most of the issues that people have had by minimizing the amount of mutexes that are around state and minimizing the amount of concurrency issues by using that one big pipe thing. That is where a lot of the edge cases come in. What you're not going to solve by doing this exercise is things like the FLP problem, or as I prefer to call it, the leader thrashing problem, where you have the timing is like, if you set up your timing wrong in Raft, the leaders will just thrash, right? So one person will say, I'm the candidate, and then the other person will say, I'm the candidate, and then they'll say, I'm the candidate, and they'll just keep trying to be candidates and just keep trying to climb the term numbers up and up. So you need to make sure you do things like have stochastic intervals for candidacy timeouts, so everyone's not becoming the leader at the same time. You need to configure your system so that you have enough time between timeouts, right? So that you have this sort of reasonable outage when you don't have a leader, but also so that the new leader can elect itself without thrashing.
Right. Yeah.
So there are problems that you'll encounter when you're running this in production, that aren't on that one pager in the Raft paper. But getting to that good quality state where you can get a leader elected, you can kill the leader and a new leader gets elected, and you can get totally ordered commands through the Raft system. I'd say that's a doable exercise.
Cool. And what happens when you've got that? When you've got you've got it working and you've got your leader up? How does it actually work when I want to actually start writing some data? Do I then just send my data packets to Raft and it has a special message that says, now I'm just writing this data? Or...
Yeah, I mean, that's actually a great question. So now what do we do with it? Well, yeah, I mean, so you're building some sort of application, right? If you just want nominate a leader and tell me where to write, probably you should just use etcd for that, or Zookeeper if you're writing in Java. But now that you have Raft up and running, you can start thinking about the application semantics of whatever you're doing, right? So the simplest thing to start with is a key value store, right? And so what you have inside the key value store is you're just totally ordering all of your puts, right? And if you want linearizability, which is the strongest form of consistency, you could also totally order all of your gets as well. So every client says, I want to put this value to this key. And then Raft turns that into a command, right? Replicates it around, it's in this log, and then it executes that command onto their local database. And then now if you have concurrent puts that are coming in, right, they are totally ordered. So you end up with that sequential consistency. This happened before this, right? This put happened before this, even if they come in different nodes. And then you can start to think to yourself, okay, well, we have this object space that belongs in one shard and this object space that belongs in another shard. So maybe now we have two Raft replicas that are working on opposite shards so that we can increase throughput. And now you have sort of a distributed key value store, that might be using, key hashing or something like that to distribute the different shards. So, now you start to think about your application. But maybe that sort of key value store is, and if the key value store, you can start thinking, okay, well, I want caching, I want eviction. So now on top of my Raft cluster, I'm going to have another process that will start to do eviction in a consistent manner, right? So eviction becomes a consensus process inside the system. And
right.
So you can start to see how anytime you want something that has a strong consistency semantic in your application, you already have this sort of underlying consensus thing running on the nodes, and you're not asking some external system to do it for you, right? You can have these internal processes that are working.
So you can literally describe the custom menu of commands you want to be rafted.
Exactly.
Yeah.
Exactly.
Okay.
Like with Arculite, right? Any insert or update is getting rafted. Any select just goes to whatever replica's underlying thing that it has, right? So you can absolutely, or you could create a lock server, right? Now, if you have a lock server, maybe you just use etcd for the lock server. But you can create a lock server if you want to do more complex key value transactions. Maybe I don't want to just do a put on X. I want to do a put on X, Y, and Z, and I want to make sure that I lock all of those keys before I put them together.
Yeah. Or you can implement your own check and swap, right? I want to put
exactly
X, provided X is currently this value.
Yeah.
Yeah.
Or maybe I want to start thinking about a file system, right? And I want to create a distributed file system, or I want to create a distributed compute system that where the executors are working on specific pieces of data, and that we have fault tolerance on the executors. And you start thinking about, well, I don't need something as massive as Yarn or Mesos or something like that, right? So now you have this little consensus algorithm that's working to manage your distributed compute. Or maybe now I want to build a graph database, right?
Yeah.
You can start to see how you start to build up how your consistency model, like what you're going to allow to have like a weaker consistency, what you might be allowed to be replicated differently versus what types of operations go through consensus and they're already on your data storage system.
Yeah, yeah. Do you know what it reminds me of? A little hack I've been playing with is like networked game engine.
Okay.
Where you have this bunch of commands, which is I'm joining the game, I'm leaving the game, and so forth. And then you've got within that session thing a packet of commands that actually relate to the game that's actually been played, like fire the missiles, for instance.
Okay.
And it's a bit like that, isn't it? It's like once you've got this base layer of session consensus management, then you can stick whatever you like in the middle of that data type.
Absolutely.
That I don't know if anyone's ever said this in history, but by gosh, you've made it sound like fun.
Well, if there's one goal I could have, it should be fun, right? I do want it to sound like fun. This is where I think Paxos struggled. Paxos focused on safety, right? Raft focused on understandability. ePaxos focus, I also recommend looking at ePaxos too. So we're talking about Raft, but ePaxos is another. There's basically two optimizations to base Paxos. Optimization one is called the leader-oriented Paxos, which is multi-Paxos, Raft, and a whole host of others. And the other optimization is optimistic fast path. And this is what fast Paxos and ePaxos do, is they basically, maybe I should back up for a second. For any consensus algorithm, there has to be two phases minimum. There has to be a propose phase and an accept phase. Minimum. You probably also have a commit phase or an execute phase, probably. Right. But there has to be a propose phase or an accept phase in order for it to be safe, right? In order for that coordination to be safe. What leader-oriented optimizations do is they just do the propose phase all at once, right? So basically the leader says, okay, I have proposed for all of the following slots, right? They're mine. Right. And so the leader, so that it just takes away the propose phase and everything after that is accept phase. So that's the leader-oriented optimization. The fast Paxos optimization is we go straight to accept and we skip propose. And if we detect a conflict, then we have to do propose accept. And so what happens is you're optimistic in that there's no conflict. You can get these accepts through and you won't detect an issue. But if there is a conflict, then you have to go through the slow path, which is a propose accept, but it actually is turned into three phases, right? Because you have that initial accept, then a propose, then an accept. So those are the two basic optimizations. Raft is the leader optimization. ePaxos is the fast path optimization.
Right, yeah, I see the optimism in there. And that must work well when collisions are rare.
Exactly.
But then you've got all the fun of writing rollback code.
You do. And actually the most complicated thing about ePaxos is that dependency thing, which gets into our point about applications, right? In order to detect a dependency, that's kind of an application level thing, right? Like, how do you figure out, like, how do you tell ePaxos, like a generic ePaxos, that this thing is dependent on that thing, right? X is dependent on Y, but not Z, right? And so that's the tricky thing. And so ePaxos is probably better used embedded into more specific applications where those dependencies are known. But ePaxos massively increases the throughput because you don't have a leader bottleneck anymore. And so you'll get much higher throughput from ePaxos at the cost of having to figure out this dependency thing.
But you can still get those strong consistency guarantees across the distributed system.
It's just as strongly consistent as Raft is.
And should we be ambitious enough to try and implement that one ourselves?
That one is tougher than Raft. Unfortunately, there isn't that sort of nice one-pager thing that Raft has. Absolutely for fun, I think you should do that. For production, there aren't as many reference implementations, right? So one thing we talked about with Raft is there's a huge number of reference implementations, right? HashiCorp, etcd, Cockroach, like there's just a huge number of reference implementations that you can look at. Not so much with ePaxos, but I would like to see ePaxos start to grow. The criticism with ePaxos is that you can't shard it like Raft, right? So Raft, you have this leader that's maxing out throughput. So if you have 3 nodes, you put 3 leaders on each of the on each of the nodes. Whereas with ePaxos, all of the nodes are maxing their throughput. So the idea is if Raft can do 5,000 messages per second, then you can get up to 15,000 messages per second with 3, whereas ePaxos can do 15,000 messages per second, but it requires all 3, right? You're maxing out the CPU of all 3.
Right.
But you don't have to shard.
Right,
Except
yeah.
that you have to do this dependency thing.
Are there particular kinds of applications where this shines?
Yes. Anything where the latency between messages is high. ePaxos was developed specifically for geographic replication.
Right.
So, my research, what we thought is, we have, vertical Paxos, which is you have a configuration Paxos and then the object Paxos or the command Paxos. If you have an ePaxos that's managing your sub rafts, right, that's actually a good way to really create a big system that goes across different regions and has privacy guarantees and provenance aware things and right. That's what we like.
Is that, that's sounding like a real nest. Is that something we can hire you to do for us? Are you busy at the moment?
I am busy at the moment, and that's exactly what we're thinking about is how do we create these sort of large distributed systems that are planet scale, and how can you replicate across them? And our sort of mode of operation is mixing and matching, right? So having some layers that are doing ePaxos, some layers that are doing Raft, some layers that are doing eventual consistency with probabilistic entropy.
Right.
Yeah, so that's how we're building our distributed systems at Rotational Labs.
Rotational Labs. Who are the clients for that? Are we talking like just the major, large geographic players, or is this something the smaller companies might need?
I think this is something that smaller companies might need right now, small and medium-sized companies. Like I mentioned, it's very easy these days to put your application into a different region and therefore grow your market, right? You have machine translation for I-18N issues, right? You have the cloud services to place your application in those countries. And it's easy to do that, but then you get into all sorts of complications once you start to manage those distributed systems. And what the cloud companies want to tell you is just use our service and it'll just work by default. My favorite example of this going terribly wrong was the Pokemon Go release by Niantic.
I missed that one. Help me out.
Yeah, so Niantic was commissioned to create the Pokemon Go mobile app, which was one of the first very successful augmented reality games, right? So, I remember we were all joking back in the day, people walking around with their phones looking for these like Pokemon,
and how you see the little monsters on the street through your phone.
Yeah, exactly. Yeah. You just use the camera and you would find these Pokemon like in the world, and there was gyms, and you could throw your Pokeball at it and capture them, and everyone's Fitbit spiked because now everyone's walking around. And it was a very successful game, but the release was highly chaotic. It was highly chaotic because I think they released in 50 countries simultaneously. Like they first released in Japan, then the US, and then it was like 50 countries.
Right.
And people were having login issues, registration issues. They weren't being able to capture Pokemon. It was like a real big issue. And when they diagnosed it, it was a distributed data system issue, right? The databases that they were using weren't replicating well. And all of these things were consistency symptoms. So they ended up hiring Google to fix the problems. And so Google brought in their sort of cloud resources and Spanner and some other things to fix the issue for Niantic, and everything went smoothly after that. And it was a great tale. But when you're a small to medium company, right, paying for Spanner is horribly expensive. And so
buying in Google is never cheap, right?
exactly, exactly. And you do have to understand. I mean, Niantic had experts help them, redevelop their application for these new global consistency models. And so, if you want to go to market in a different region, right, I think you do have to consider this problem because you are going to have issues if you're selling something and there's an inventory issue, and is it fair that whoever in whoever's closest to your server gets the best deal, right? Like you don't really want that to happen. So you want to make sure that you have a distributed system set up well, and we're certainly interested in making sure that people can do that.
And there are increasing number of companies trying to do that, right, across the globe,
Yeah,
because it's initially so easy and obviously business desirable. But the devil's in the details.
The devil's in the details, and you don't know necessarily where your product is going to land or where what you're doing is going to be gain the most traction. So it is important, I think, for companies to branch out besides just their local regions.
Yeah. Years ago, I sold a software thing, and it turned out my best market was Austria. Far and away. Didn't see that coming. How do I target Austria?
Yeah, I love stories like that.
Well, from here in the UK to there in the US, our distributed system must come to an end. Benjamin, it's a pleasure talking. We could talk. We might have to have a sequel. Maybe we'll try and be in 2 different countries for that one. You can be in Australia, I'll be in Singapore or something.
There you go.
Thanks very much for joining us. It was a pleasure.
Thank you for having me.
Thank you, Benjamin. And as I said at the start, that really has inspired me to do some coding. And if you caught our episode a few weeks back on Erlang and Gleam, I'm thinking actors, I'm thinking sending messages to a single serializable point, I'm thinking predictable failure modes. This might be the Gleam project I've been looking for. I'll keep you posted. If I manage to get that together, I'll let you know. And if any of you out there break out an editor and put something together, please let me know. But you don't have to start a repository to get in touch. My contact details are in the show notes, as always, and the comment box, the like button, the subscribe button, and such, they're always there for you. Send your feedback across the globe, and my inboxes will linearize them for you automatically. And also take a look in the show notes if you want to check out Rotational Labs and see the problems that Benjamin's actively solving with all these techniques. And you can also look in the show notes for links to the original Raft paper and a few related papers that might tickle your fancy. And I think that brings us to the close of this consensus slot. I've been your host, Chris Jenkins. This has been Developer Voices with Benjamin Bengfort. Thanks for listening.